excited to be there virtually with you today and to share a little bit about my work on aligning human and robot representations. So this is sort of what I work on. I develop robot algorithms that learn from people from a variety of different forms of data from them. And I do that because I really believe that if we want robots to not just live in a vacuum, they have to be capable to adapt to the people that they interact with. And as a running example, let's imagine this Jaco robot wants to carry this mug over to my colleague on the left. And so Jaco can generate a trajectory xi that optimizes some pre-specified reward function r. Now in robotics, typically this reward function is parameterized by a theta that encodes a trade-off between important features phi of the task, things like the cup orientation, the distance to table, or efficiency. Now Jaco starts off only caring about being efficient, so it follows the shortest path trajectory from start to goal. But then I noticed that it's carrying the cup a little bit too high up above the table. So what I can do is I can push on it to correct it. And now the robot can use my correction to adapt to how I wanted the task to be done, and thus produce a new trajectory that stays closer to the table this time to hand over the mug to my colleague. So this is one example of robots adapting to people. I recently finished my PhD at UC Berkeley, where my brilliant AI colleagues similarly thought about getting robots to do hard tasks for humans. And as an example, here they really wanted to create a robot butler that can serve wine to customers. And they came up with something like this. Now, from an AI perspective, this is an amazing feat of robotics. You have this robot that can move incredibly fast without spilling a single drop of wine, nor breaking the glass. From a human user perspective, though, I don't know about you, but if this is how the robot acted around me, I would be personally pretty terrified. So while this robot achieves something that's very technically impressive, it fails to consider that a real customer, a real human, would probably be too startled and not too satisfied because they'd be too scared of the robot spilling or breaking the glass or smacking them and so on. And so we're seeing this amazing progress for getting robots to work in isolation, but we're still pretty far from getting them to work around people. And we see consequences of this all the time in the news. On the left, there's this Uber crash in Arizona where the autonomous car fatally hit a jaywalking pedestrian for the simple reason that it didn't understand the wild concept of jaywalking pedestrians. It only knew about pedestrians at crosswalks. And then on the right-hand side, you kind of have the flip side situation where this time the human pilot didn't know about a new feature that was programmed into the flight control system. They didn't understand what it was doing, which caused them to enter a tug of war and ultimately nosedive into the ocean. And so human-robot interaction is still really hard. And to understand the reason underlying all of these failures, I'd like to share with you an example of failed human-human interaction.
Okay, does this row have more quarters? Does this row have more quarters, or are they the same?
The same.
The same? Okay, now watch. Now, does this row have more quarters? Does this row have more quarters, or are they the same?
That one has more quarters.
That one has more quarters?
Yeah.
Why does that one have more quarters?
Because it's stretched out.
So here, this child is clearly missing something, right? He's missing this concept of conservation of certain properties like count. Very normal for a child this age. But without understanding this concept, the child is making the wrong inferences and giving the wrong answer. And not only that, but he's then able to explain his wrong answer using all these other concepts he knows about that are actually pretty unrelated. In that sense, our robots are still a little bit like little children. Let's say that this time I actually want the robot to stay farther away from my personal laptop, but the robot has no notion of distance to laptops. And without that, it can't learn well from my push, and even worse, it latches onto other features to do its task, similarly to how the child was latching onto all those other concepts to answer the question. So in my view, one of the biggest obstacles currently to successful human-robot interaction is the fact that these representations are more often than not misaligned. And that's why in our work, I've been tackling what I call the representation alignment problem. How can the robot align its representation with that of the human that it's interacting with and learning from? And so far, we've seen a more traditional solution to this question. where you have a system designer that uses their domain expertise to just hand specify these feature representations, and then the robot can use that to learn a reward function on top of them from human inputs like corrections, maybe demonstrations, language, and so on. And then the robot can optimize this reward to produce a trajectory in the world. This is all great, but unfortunately, it does require hand specifying every single thing ahead of time. And it's pretty unreasonable to assume that a system designer can think of what any human in any environment for any preference and any task could possibly care about ahead of time. There's a simple solution to this. Why not just learn the features as well? After all, that is what the deep learning revolution has enabled us to do. So let's try that and see what happens. So if the person cares about staying close to this table and far away from a laptop, spatially the reward function might look something like this, where it's really low when you're right above the laptop and high above the table, and it gets better and better the closer to the table and farther from the laptop you look. Now, when the robot is missing some feature like distance to laptop, deep learning tells us that we can just model what's missing with a neural network, collect some demonstrations from the human for how to do the task, and then use them to both extract what's missing and the reward kind of both at once. And this is kind of what we get. It turns out that we vaguely learned that being around the laptop is bad, but we don't really learn these more fine-grained causal details of the reward function. And that's because these demonstrations, they're meant to teach the robot how to do the task. They're not really meant to teach it about the feature or about the representation per se. And so here, the neural network is only hoping to extract information about the missing feature implicitly from these demonstrations. But by trying to do kind of both things at once, deep learning ends up generalizing pretty poorly. The implication is that now, when I optimize this reward, I get some pretty suboptimal behavior from our robot in contrast to how I would want the task to be done. So, as a summary, one paradigm learns good rewards but requires handcrafted representations. The other one bypasses handcrafting but does a pretty poor job generalizing. So, can we somehow bridge the gap between these two? And rather than assuming a representation or hoping that you'll just pick it up along the way, a core idea in my work has been that robots should just directly engage with humans in an interactive process for arriving at a shared representation of their task. This has led to a divide and conquer approach to robot learning. Let's first focus explicitly on learning the representation from human input, and only then use that representation for learning the downstream task. And what's really nice about this is that I don't need to rely on, I'm not stuck on demonstrations anymore. I actually have this opportunity to design new human input AHV that is explicitly targeted at teaching you the representation itself and can do that effectively. And so today I'll share with you a quick taste of 3 different components that play a critical role in formalizing representation alignment in HRI. And I'll mostly focus on the first one, this question of how do we learn representations from humans? And coming back to this example, what if we applied our divide and conquer philosophy and first focused on learning the feature itself by asking the human for some sort of mystery input about it, and only then learn the reward on top using inputs like demonstrations or corrections? The key question, though, is what is this mystery representation specific input that's going to help us out here? Well, one idea is to just naively ask the person for labels representing the feature value at different states in the state space, and just use those labels to supervise directly the training of the neural network. The problem is, as you can imagine, to cover such a large state space, the robot would need a ton of labels from the person, which is way too burdensome. So that's not really a feasible approach. Even worse, though, people are pretty imprecise when labeling states directly. Something like 0.32 doesn't exactly come natural for us as a form of feedback. We can, though, address the second problem by instead asking the person to provide relative labels, comparing the feature values in pairs of states across the space. And so now you can train the neural network with what is called the Bradley-Terry model for pairwise comparisons. The problem is that you still need a ton of comparisons to cover the space. So my take on this is that humans are actually a lot more intelligent and capable than just giving us 0, 1 labels, so long as we give them the right way to give us data. And so what we wanted here was to come up with some sort of feature input that is really informative for the robot, while at the same time not placing too much sample complexity burden on the human. So our idea here was that we can pack a lot more information if we ask the person for a sequence of states with feature values that are monotonically decreasing. We called such a sequence a feature trace, and now the robot can automatically extract comparisons from this trace by exploiting the monotonicity. I'll get back to this in just a second, but in practice, if I want to teach the robot about distance from laptop, I start somewhere where the feature is highly expressed, so right above the laptop, and then I move the robot monotonically towards a place where the feature is not highly expressed, so away from the laptop. And now the robot can collect a few of these traces and learn a feature function that's defined by them. So now, how does the robot actually learn from these traces in practice? Well, it does so by exploiting its assumptions about the feature traces that it knows. So first, we know that they satisfy monotonicity, where the feature values decrease along the states of the trace. And what this means is that I can take any ordered combination of 2 states along a trace and label that as 1, meaning that the first state has the higher feature value. And what's really special about this is that for every single trace, we end up with a number of tuple comparison queries that is quadratic in the length of the trace, which is a ton of data. So for 1 feature trace, I can get somewhere around 200 to 300 comparisons, which is already an immense amount of data. Now, we can also relate the feature values across the traces, because we also know that all the traces start approximately high and they end approximately low. So for any 2 traces, what this means is that the feature values for the starts need to be consistently high, and the same for the feature values for the ends, they have to be consistently low. And this gives us equivalence tuples with a label of 0, 5 that symbolizes equal preference between the starts and between the ends. And so now we can incorporate this data set of tuples into a cross entropy loss based on this Bradley-Terry model up top and just train our neural network function. And I'd like to share with you some examples of features that we managed to learn this way using traces from both expert users as well as non-expert users in the user study. And for all evaluations, we sampled this very large set of test states around the robot's reachable set, which we color here with the feature value. So here I'm showing the distance to laptop feature. And for easy visualization, I can also project this feature onto some representative like here. So when we look at the ground truth for the laptop feature, we see this projected ball that decreases in intensity the farther we look from the center of the laptop. And when we trained the model using collected traces from the expert, we ended up with something that's very structurally similar to this. And in fact, this result kind of holds across 6 different features that we looked at of varying complexity. And the nice part about this is that these features are trained with somewhere along the lines of 10 to 20 feature traces, not the thousands of demonstrations that the end-to-end approaches would have required. Now, I'd like to also share some examples from our user study, because we also care about can real people use feature traces to teach their robots. So for the laptop feature, we similarly see that users gave these traces that start above move away. And so we recover this projected ball over here that looks very similar to what we saw in the previous slide. For table, they covered the space vertically from up to down. And what I found the coolest personally was this proxemics feature, which is this notion that people really dislike having things in front of their face more so than to their sides. And our novice users figured out on their own that the optimal way to teach this is to give these longer traces in front of them and shorter to their sides to kind of indicate this higher penalty in front of their face. And so we saw this core idea in action, but asking humans for data is quite expensive. So kind of behind the scenes, another key principle that we've been employing is trying to learn a lot from a little. And we saw this with feature traces where we created data that is packed with information, but super easy and quick for the person to give. So I'd like to share a few more examples, more cursorily, of learning a lot from a little and how this idea generalizes over and over. So first, we tried extending representation learning to higher dimensional inputs like images or point clouds, which can be notoriously data hungry. And here the idea for learning a lot from a little was to still collect a small amount of labels from the person, but amplify them using simulation. And so if the human wants to teach a feature like near, they can label different images as this is near, this is not near. And then we can spawn many different objects in a simulator and augment these labels into a data set of thousands and thousands of examples for free. And that enabled us to learn pretty robust features like objects being near or above each other that were able to transfer to the real world without any additional human data. And importantly, without any real human data, all the data was in the simulator. We also looked at learning more complex, fuzzy, difficult to define features like emotion. And specifically, we wanted our robot to exhibit expressive behavior like tiptoeing to its goal when afraid or stomping aggressively when angry. Emotion, though, as you can imagine, is a very subjective and thus very challenging feature to convey to our robots. But luckily, cognitive scientists have made this a little easier for us. And they found that all emotions live on this three-dimensional valence arousal dominance spectrum. And because of this really nice structure, we were actually able to learn a mapping from these expressive robot behaviors on the right to this three-dimensional emotion representation with just a few labels from the human. I think we required half an hour, 20 to 30 minutes of human training to learn a whole representation. And the bonus to this is that this representation can easily be plugged into language models. So we were able to generalize to new phrases that were never seen before, like great weather today or didn't get the offer. Finally, we learned features by using common sense priors, like the ones that come from large language models or LLMs. And specifically, we had a human demonstrate, in this case, throwing away the can in two different scenarios. And then we asked the robot, why were these two behaviors different? Now, to us, it's pretty common sense that the human didn't want to step on electronics, so the feature distance to electronics is pretty important. And it turns out that LLMs are also really great at finding these hidden features, even though the human didn't explicitly say anything about it. And so we equipped our robot with an LLM to find these hidden features from observations of the human, and it was able to generalize to these new unseen situations any additional human data. So now that we've seen how it can learn features one by one, how would the robot even know when its representation is misaligned in the first place? How would it know that it's missing something? And so we'll go back to this scenario in the beginning and remember that that without knowing about this feature, the distance laptop, the robot is just sort of blindly learning something else. It was learning to stay close to the table. I don't want this to happen. Instead, is there a way in which the robot can autonomously figure out that my push, my correction, refers to something that it just doesn't know about yet? Well, since when people act, they don't just do so randomly, we use the so-called Boltzmann noisily rational model from cognitive psychology to model people as selecting inputs in proportion to their exponentiated reward. Kind of a fancier version, a more advanced version of the previous Bradley-Terry model that we saw. And what's really interesting about this model is specifically this coefficient beta over here that models how rational or optimal people are. Typically in robotics, this beta is fixed to something reasonably high, essentially assuming that people will be reasonably rational and all their inputs should be trusted because they're teaching you. But since we're specifically trying to detect misalignment, we're actually not going to do that. And we instead going to estimate this beta and reinterpret it as a confidence for how well the robot's representation can explain the human's input. And we're going to infer it along the way jointly with theta, the reward parameter. And so what this means is that when the human and robot representations are aligned, the robot estimates a high confidence on the correct intent theta that explains the human's input. And so it can learn assuredly from the person's feedback. However, when they're misaligned, the robot estimates a low confidence across its representation. And so it's not going to learn from inputs that it does not trust and that it sees that no possible hypothesis data is peaking up. And so back to our beginning example, this time, when I push, the robot infers a low confidence, which maps to no longer incorrectly inferring or learning to stay close to the table like before. Importantly, this is not something that we hand tune. This is something that automatically happens. The robot is automatically monitoring its confidence and kind of can learn in proportion to it. Or you could also imagine modifying this to just get the robot to just simply stop if it has low confidence in safety critical situations. We compared the method in a with real users in a study, and we see that in this situation, there's no misalignment. Both the robot and the human know about distance to table, so both methods learn assuredly from the human's input to stay closer to the table, so there's no issue here. When things get more interesting, though, is when there is misalignment. So this time, the robot knows about cup orientation, not about distance to table. So what you're going to see is the human down, but the robot is learning incorrectly to tip over the cup. So not only does the human have to keep pushing down to try to teach the robot, they also have to correct for the robot's incorrect learning additional on top of that. Meanwhile, with our method, because we're able to estimate this low confidence, we're able to stay robust to unintended learning. We're not incorrectly learning to tip over the cup, so the human doesn't have to keep correcting for that. Obviously, this doesn't mean the robot magically knows how to keep the cup close to the table yet, because it hasn't learned a feature about that yet, but we are able to stay robust to unintended learning. And this framework generalizes beyond corrections to demonstrations, teleoperations, and so on. Lastly, to then properly learn from and interpret people's task input, the robot needs a model for how people make choices. And we sort of already saw this Boltzmann model, but we found this model to be quite unintuitive. And we actually found the more natural way to model people is to use human-aligned representations that adjust for the similarity that these potential trajectory choices in their head have. And I'm kind of glossing over this, but we did run a user study that showed that people themselves choose in a way that's more compatible with our model than with the Boltzmann model. And this suggests that this model can be useful beyond robotics, to cognitive science and to econometrics. And so now kind of putting everything together, and we're looking at some examples of reward functions that we can learn with these methods. We see that our divide and conquer approach over here recovers much more generalizable rewards than the end-to-end approach. This means that now the robot can do the task in the way that I want it. It can stay away from my laptop and stay close to the table too. To close off, we sort of started by putting forward this vision of engaging with people in an interactive process for arriving at shared representations. But this work that I've talked about today has really only looked at this very standard approach, which has the human in the teacher role feeding the robot data about their representation. In reality, though, I really believe that seamless human-robot collaboration demands more than just passive data absorption. This really should be a bi-directional process where the robot is an active participant in the interaction. There's a lot of research directions that come out of this. I'm going to skip over them, but I'm super excited about all of these directions that are possible because we're explicitly tackling representation alignment rather than just hoping that they're just going to naturally emerge on their own. I'd like to thank all of my collaborators. I'm happy to take any questions. Thank you.
All right, thank you. Any question here? Let me see if I have a question online. All right, so actually I have a question. So I noticed that the kind of tasks you have focused on, right? So they are continuous space, relative low dimensions, and it's mostly about robot arm kind of manipulation. I think you have one demo about the mobile kind of robots. Do you see like if we want to generalize to more kind of open-ended kind of situations where you have much higher dimension kind of space, different kinds of tasks, different kind of robots. Do you see any kind of a challenge for aligning the representation in those kind of situations?
Yeah, so if I interpreted your question correctly, is it really scalable or feasible to like learn features one by one, especially when you go to higher dimensional tasks where your representation might just have more and more features? Is that kind of what I'm hearing from you?
Yes.
Okay. Yeah, so I kind of two answers to this. One, I kind of think of these features of something they're meant to be reusable from task to task. So I kind of think of something like distance to laptop or distance to electronic device or something like that as something that is not meant to just be used once for this one task and then be discarded. So I kind of think of the robot building a repertoire in its representation of things that matter. The second part to this, the second answer to this is that we actually have looked at approaches more recently that instead of trying to learn the feature one by one, is trying to kind of learn the representation all at once. And so we do have some approaches for just like learning the whole representation rather than doing it one by one. There's a few issues, there's a few downsides to this, which is that you will get a representation that is more entangled than if you were to manually separate the structure into different features. But there is the advantage that the human might not need to explicitly